All right, next let's take a look at problem 6. So problem 6 asks about the applicability of the Virial equation of state. And so you're asked if the Virial equation of state is applicable at 3 different conditions at the same pressure. So before we look at the question in detail, so just know, I understand that this is a question in which it's difficult to give a very precise answer, or necessarily, especially as a student in the class, to give a very confident, precise answer. But the goal of this question is to get you to think about the range of applicabilities of the equations that we'll tackle. Right, and so in general, I would tell you that if you had to predict the phase behavior of a fluid, say at a given temperature and pressure, use a cubic equation of state, because that's going to be applicable to both liquid and vapor phases. Okay, truncated Virial equation. So remember, the challenge is when they mention truncated Virial equation in the text, typically they're talking about inclusion of a second Virial coefficient. So essentially, Virial coefficient would be a Taylor series expansion for Z truncated after the second term. Right, so it's going to be a first order correction to my ideal gas limit. Right, and as such, the Virial equation is going to be limited to cases for which my deviations aren't too far away from your ideal gas limit, because essentially all it's doing is, drawing a tangent to that ideal gas limit and extrapolating. Okay. Remember, the benefit of the Virial coefficient is the Virial equation is our only theoretically based equation of state. It's just a matter of, for most practical applications, it's going to be limited just due to the availability of parameters. Okay. So in problem 6, determine whether the truncated Virial equation is valid for ethane at the following states. And again, we have 3 different states, all at 10 bars. And then in terms of additional data, we're told the boiling point of ethane at 10 bars is negative 29 degrees C. Okay, and so that would say directly be applicable to B, because we would be at negative 29 degrees C when we have a saturated vapor. All right, so difficult, question in terms of giving a very precise answer. But again, I just want you to try and think about the applicability of your equation, and to try and come up with your best estimate. And so the general idea again is, remember, in the text, truncated Virial equations interpreted as Virial equation truncated after my second term, so inclusion of my second Virial coefficient. So you could think of this as a Taylor series expansion about your ideal gas limit, truncated after your first term. Okay. We also said, for a given temperature, so if temperature is fixed, you could think of this as a Maclaurin series expansion about the ideal gas limit, P is equal to 0. And so I'm going to flip over to our notes from the chapter, namely our Z versus P phase diagram, and then our Z versus P phase diagram in reduced coordinates to give you an idea of exactly what this means. Okay, so if you want to think of this, or you should think of this or interpret it as a Taylor series expansion about your ideal gas limit, P equals 0, at a given temperature. So essentially what we're doing is, for your temperature of interest, okay, you can look at the relevant isotherm. And so then the assumption is that I'm drawing a tangent through my ideal gas limit and extrapolating. Okay, so what you can see is if I'm in this superheated vapor region, then let's see if I can zoom in a little bit. So if I'm within the superheated vapor region, right, it might be reasonable, right? It'll be reasonable over these narrow ranges of pressure to take my to assume that my that the Virial equation would be applicable, right? So basically, here is Z versus P. So what I'm assuming is I'm drawing a tangent about my ideal gas limit. So I'm assuming Z is linear over this region with a slope equal to that at the ideal gas limit. So it might be reasonable in the superheated vapor region to assume that is the case. Although, right, even at, say, this T2, right, you will notice some curvature, right? It's not exactly straight. Okay, so remember, this is high temperature down to low. So at low temperatures, right, it looks like it's much more linear over that superheated vapor region, but that's also partially just because of that temperature range or that pressure range is a lot smaller. Whereas if I go up here to my critical temperature TC, right, and then that one just below it, over that wide temperature range, there's definitely some obvious curvature, and so you would suggest that there'd be some errors in the applicability of truncated virial equation. So what's shown in the second graph, which would be more applicable to this problem, is this plotted in reduced coordinates. So where you get this abrupt change, right, is where you would hit your phase diagram. Okay, and so what's going to happen? Okay, right, and you can kind of see it. The real high temperatures above TC looks a little more linear in that superheated region. But if I had a liquid phase, right, virial equation is definitely not going to be applicable, right, in terms of an extrapolation from this point. So what you're going to need to do for ethane is you can go to the back of the book and you can look up TC and PC, and what the critical temperature and pressure for A, B, and C. You can go and you can calculate your reduced temperature and pressure, and that's just to give you. So then, if I were to look at, say, this sketch, your reduced temperature, right, will give you an idea of what isotherm you're essentially on, and then your reduced pressure will give you an idea of where you are on that curve with respect to the ideal gas limit. And so then the question, it just becomes a judgment call of if I were to fit a tangent line to the ideal gas limit for that isotherm, would that be a reasonable approximation for my state of interest? So if, say, I'm at a reduced temperature of 1, and let's just say I have a reduced pressure of 0.5, all right, if I were to try and, say, put a piece of paper on this plot, so this is figure 2.7 in your book, right, I would guesstimate that, your tangent line, say, would come out somewhere around here. All right, this is me with the best of my abilities with my mouse, right, and so there, then, truncated virial wouldn't be applicable. If I was on this reduced isotherm of 1.2 and I were to go through the same exercise, well, yeah, there it looks like perhaps it would be reasonable if I were to draw a tangent. Okay, so that's essentially what I want you to do is try and figure out the reduced coordinates for A, B, and C, and then look at that reduced phase diagram and try and come up with the best estimate of terms of whether or not you think it would be applicable or not. Again, this is just trying to get you to think about the applicability of the equation. And if I look at, say, point C, right, spoiler alert, right, so if, at 10 bars, Tsat's negative 29 degrees C. If I'm at negative 35 degrees C, I'm going to be in the subcooled liquid region. So I know in C that equation of state, or the virial equation, definitely won't be applicable. B, you'd have to look up the reduced temperature, but I know C, right, I'm going to be sitting somewhere like this, right on my phase envelope, and just based on this TR of 0.9 and TR of 1, right, that's definitely not going. The virial equation definitely won't be a good estimate at saturation, right, if I'm just extrapolating from that ideal gas limit. Okay, but again, figure out the reduced coordinates and try and estimate for yourself. Maybe there's hope. You'll just have to figure that one out. Hopefully that helps.